Tonight, the story follows a black hole so vast that it almost resists belief. Far beyond the nearby universe, astronomers find a cosmic giant hidden inside one of the brightest beacons ever seen. A black hole with a mass so extreme it changes the sense of scale itself. This journey moves from the largest structures in the cosmos to the silent edge where light can no longer return. If this kind of deep space mystery belongs on the channel, please like, subscribe, and share the video so more curious minds can find it. The observable universe extends in all directions with no visible edge, a vast expanse filled with galaxies, clusters, and the faint glow of ancient light. Within this immense scale, structures vary in size from small groups of stars to systems that stretch across millions of light years. Among these structures, galaxies gather in clusters, and clusters gather into larger patterns, forming a network that appears almost like threads of light against a deep, dark background. In this setting, distance is not only space but also time, as light takes billions of years to travel from distant objects to the point of observation. Within this broad environment, black holes exist as one class of object among many. Most galaxies contain a central black hole, often described as supermassive, with masses ranging from millions to billions of times the mass of the Sun. These black holes remain hidden from direct view, as they emit no light of their own. Instead, their presence is inferred through the motion of nearby stars and gas, or through the light produced when matter falls toward them. Even at these scales, such black holes are considered large, yet they remain small in comparison to the full size of their host galaxies. Far beyond the familiar range of nearby galaxies, astronomers observe a smaller population of objects that stand out for their unusual brightness. These objects appear as intense points of light, visible across vast distances. Their brightness suggests an energy output far greater than that of ordinary stars or even entire galaxies. Through careful observation, it becomes clear that these distant points are not simple stars, but the luminous centers of galaxies in an active state. In these cases, matter flows inward toward a central black hole, releasing energy as it heats and accelerates. Among this population, a few objects display properties that place them at the extreme end of known measurements. One such object is associated with a black hole, whose estimated mass reaches tens of billions of times the mass of the Sun. This scale exceeds the mass of most known black holes and approaches a level that seems difficult to reconcile with typical models of growth. Observations indicate that such objects existed when the universe was much younger, suggesting that their formation occurred over relatively short cosmic timescales. To understand this scale, it is useful to consider the relative sizes involved. The Sun contains most of the mass in the solar system, yet it is only one star among hundreds of billions in the Milky Way galaxy. The central black hole of the Milky Way has a mass of about 4 million times the mass of the Sun, which is already considered large in comparison to stellar remnants. However, a black hole with tens of billions of solar masses exceeds this by several thousand times, placing it in a category often described as ultramassive. Despite this immense mass, the black hole itself occupies a region of space that remains small relative to the size of its host galaxy. The gravitational influence of the black hole extends outward, shaping the motion of nearby matter, but the visible extent of the galaxy spans far beyond this central region. The contrast between the compact nature of the black hole and the vast scale of the galaxy highlights the unusual concentration of mass within a limited volume. At the largest scale, the presence of such a black hole does not disrupt the overall structure of the universe. Galaxies continue to form and evolve. Clusters remain bound by gravity, and the large-scale structure retains its filament-like pattern. The black hole, though immense in its own right, is one component within a broader system. Its significance lies not in altering the entire cosmos, but in representing an extreme example of what gravity can produce under certain conditions. Observations of these distant objects rely on instruments that detect light across different wavelengths, including visible light, radio waves, and X-rays. By analysing the properties of this light, astronomers estimate the mass of the central black hole and the rate at which it consumes matter. These measurements depend on models that connect the observed brightness and motion of gas to the underlying gravitational force. While these methods are widely accepted, they carry uncertainties, particularly at the highest mass ranges where direct measurement is not possible. Even with these uncertainties, the existence of such massive black holes is supported by multiple lines of evidence, spectral lines, which show how light is spread across different wavelengths, reveal the speed of gas moving near the centre. Faster motion implies stronger gravity, which in turn suggests a larger mass. The consistency of these observations across different instruments and methods strengthens the conclusion that these objects are indeed among the most massive known. In this outermost view, the black hole remains distant and abstract, defined by its place within the cosmic landscape. It appears not as a hole, nor as a dark sphere, but as a point of extraordinary brightness embedded in a field of countless other points. Its true nature lies hidden behind layers of distance, time, and intervening matter. Only by moving inward, step by step, can its structure and behaviour begin to take form. The vastness of the universe provides the context in which such an object exists. Without this scale, the significance of its mass would be difficult to grasp. Within a smaller setting, it might seem dominant, yet within the full expanse of cosmic structure, it becomes one element among many, defined by comparison and contrast. Its presence reflects the range of possibilities allowed by gravity and time, extending from the smallest particles to the largest bound systems. In this way, the black hole is both extraordinary and consistent with the broader patterns of the universe. It follows the same physical laws that govern stars, galaxies, and clusters, yet it does so at an extreme that challenges simple intuition. Observations indicate its existence, measurements suggest its scale, and models attempt to explain its growth. At this stage, it remains a distant point within an immense field, waiting to be examined more closely by moving inward through the layers that surround it. The black hole remains far away, and the distance to it is so great that ordinary measures of travel lose meaning. No ship can approach it. No human lifetime can bridge the span. The only thing that crosses the gulf is light, moving at a constant speed through expanding space. By the time that light arrives, it carries an old report. It does not show the object as it is now. It shows the object as it was when the light began its journey, deep in the earlier history of the universe. This is one of the quiet rules of astronomy. To look far away is to look back in time. Nearby planets are seen minutes in the past. Nearby stars are seen years in the past. Distant galaxies are seen millions of years in the past. The most remote bright sources are seen from a time when the universe is still young compared with its present age. Distance becomes a kind of archive. Every beam of light is a record preserved by motion and delay. The black hole associated with one of the largest known masses is observed through light that has travelled for more than 10 billion years. That statement is simple in form, but its meaning is wide. The light leaves when the universe is much younger, when galaxies are still growing rapidly and matter is flowing inward on large scales. The object therefore belongs to an earlier cosmic setting. It is not being studied in a mature universe like the one seen in the local sky. It is being studied in an age when conditions are different, when fuel is more abundant in many regions, and when some of the most luminous galactic centers are more common than they are now. Even this description requires care, because astronomers use more than one measure of distance. One measure is light travel time, which tells how long the light has been on its way. Another is the present-day distance that takes into account the expansion of space during that journey. As the light travels, the universe itself expands, increasing the separation between source and observer. Because of this, the object is now much farther away than a simple multiplication of time and light speed might suggest. Observations indicate the journey of the light lasts more than 10 billion years, while the present-day separation is much larger still. Both statements can be true at once because the space between the 2 points does not remain fixed. This expansion leaves a visible mark on the light. As space stretches, the wavelength of the travelling light stretches with it. A wavelength is the distance from one crest of a light wave to the next. When that distance grows longer, the light shifts toward the red end of the spectrum. Astronomers call this redshift. It is one of the clearest signs that the source belongs to the distant universe. The greater the redshift, the more the light has been stretched, and in general the more ancient the view becomes. Redshift is therefore not only a measure of motion or expansion, it is also a measure of historical depth. In the case of an extremely distant quasar, the redshift is large enough to place the source in a period when the universe has already formed many galaxies, but has not yet reached anything like its present age. This matters because a black hole of enormous mass must be understood within its own era. A mass that seems difficult to explain today may have grown under conditions that are less difficult in the young cosmos, though still not fully understood. The timing does not solve the puzzle by itself, but it sets the stage correctly. It places the object in a universe that is active, crowded with gas, and still assembling large structures. The light that arrives does not travel through emptiness in a simple way. Along its path, it passes through regions of thin gas, fields of gravity, and the broad fabric of expanding space. Some wavelengths are absorbed by matter between galaxies. Some may be altered by intervening material in ways that leave faint signatures in the spectrum. Yet enough of the signal survives to preserve the identity of the source. This survival is one of the remarkable facts of observation. A beam emitted from a small central region of a distant galaxy can cross almost the entire visible history of the cosmos and still arrive with information about motion, temperature, composition, and power. Because the source is so distant, brightness alone can be misleading. A very bright object seen at great distance must be producing an enormous amount of energy, but the exact relation between apparent brightness and true power depends on distance, expansion, and the spreading of light over space. Astronomers therefore combine brightness with redshift and with detailed features in the spectrum. They do not simply look at a bright point and assign a mass. They reconstruct the past conditions under which that light was emitted. The result is not a direct photograph of the black hole itself, but a physical reading of ancient radiation. Time also introduces uncertainty. The object may have changed after the light now being observed first departed. It may have grown further, dimmed, or shifted in activity. It may even look very different in the present cosmic moment. Observations cannot yet answer that present tense question because the newer light has not arrived. This is not a weakness in the method. It is the method. Astronomy accepts delay as part of reality. Knowledge of the distant universe is always historical knowledge. assembled from signals that take time to cross space. In this early epoch, galaxies often contain more cold gas than many nearby galaxies do today, and interactions between galaxies may be more common in some environments. These broad conditions are important because they help explain why the distant universe contains many powerful active galactic centers. The black hole is therefore not isolated from cosmic history. Its observed state belongs to an age of growth and movement. The ancient light preserves that age within itself. Seen in this way, the object becomes more than an extreme mass. It becomes a message from a young universe. Its photons leave long before Earth forms its present landscapes, long before human observers exist, and long before the instruments that detect them are even imaginable. They travel through expanding space without haste and without pause. At last they arrive as a thin, measurable stream, entering mirrors, detectors, and spectrographs on Earth and in orbit. What appears in the sky as a distant point is therefore also a delayed event, still unfolding at the moment of observation. The black hole remains unseen in any ordinary visual sense. What is seen is ancient light, stretched by the growth of the universe and delivered across more than 10 billion years. The light establishes the era, the distance, and the historical setting. It tells that the source belongs to a much earlier cosmos, and that every conclusion drawn from it must begin there, in time before the present, carried patiently by radiation through the largest spaces known. From the scale of the universe and the age of the travelling light, attention narrows to a single direction in the sky. At this stage, the black hole still does not appear as a dark opening or a visible sphere. It does not stand apart with a clear outline. It enters observation in a more modest form, as a distant source of light recorded against the wider background of the heavens. In the earlier stages of discovery, objects of this kind are not known by their nature. They are known first by their appearance, by their position, and by the unusual character of the light they send. The night sky seems calm to the unaided eye, but careful observation shows that it contains many kinds of objects. Some are nearby stars in the Milky Way, some are faint galaxies, some are planets that move slowly against the background, some are remnants of older explosions. When telescopes gather more light and detectors sort it with greater precision, the sky becomes less simple. Points that seem alike from a distance begin to separate into categories: brightness, colour, motion, and spectrum all help reveal what kind of object is present. A spectrum is the spread of light into its component wavelengths. It acts like a physical fingerprint. When the light of a distant source is divided in this way, certain patterns appear. Some wavelengths are stronger, some weaker, some are marked by emission, meaning extra light is released at specific wavelengths. Some are marked by absorption, where light has been removed by gas between the source and the observer. These patterns show what kinds of atoms are involved and how quickly the material is moving. Long before the central black hole can be described, the light already begins to describe the environment around it. In the middle of the 20th century, surveys of the sky began to reveal bright radio sources whose visible counterparts looked almost star-like. They were compact in appearance, yet their spectra did not match those of ordinary stars. Their redshifts were also large, placing them at great distance. This combination was striking. Something that appeared almost point-like was in fact extremely far away, which meant it had to be extraordinarily luminous. Such sources came to be known as quasars, a shorter name formed from the phrase quasi-stellar radio source, because they resembled stars in shape while differing greatly in nature. Even this name reflects the path of discovery. The source is identified first by appearance, then by puzzle, then by interpretation. To the eye of a detector, a quasar does not immediately announce a black hole. It announces excess brightness within a very small apparent area. Its light is concentrated, its distance is large, its spectrum is unusual. These clues together suggest that the source is compact and powerful at the same time. A normal star can be compact, but not powerful enough. A galaxy can be powerful, but not compact in appearance at such distances. The observed point therefore forces astronomy toward a new explanation. The direction in the sky becomes important because repeated observation must return to the same source. Position is measured against the surrounding field. Telescopes record where the object lies relative to nearby reference points. Over time, different instruments examine the same location in different parts of the spectrum. Optical telescopes study visible light. Radio telescopes detect longer wavelengths. Space observatories examine X-rays and other energetic radiation that the atmosphere blocks. Gradually, many separate observations begin to converge on one object. At this scale of observation, the host galaxy may not be easy to see. The central light can overwhelm the dimmer structure around it. The source therefore seems isolated, almost detached from a larger body, even though it is actually embedded in a galaxy. This creates one of the central visual impressions of a distant quasar. It is not seen as a grand spiral or a smooth elliptical shape. It is seen as a brilliant point that hides much of its own setting. The brightness itself becomes an obstacle to seeing the surrounding form. Brightness must also be interpreted with care. Some objects appear bright because they are nearby. Others appear bright because they are intrinsically powerful. In the case of a very distant quasar, the second explanation dominates. The source sends out such an enormous amount of energy that it remains visible across billions of light years. Its apparent point-like nature does not mean it is small in every sense. Rather, it means its most luminous region is compact enough and bright enough to dominate the image received by telescopes. The light from such a source is often steady on human timescales, yet detailed study may show variation. A change in brightness over months, weeks, or even shorter periods can reveal something about the size of the emitting region. A very large region cannot change all at once because light itself takes time to cross it. A compact region can vary more quickly. This principle gives astronomers another tool. It allows the behavior of light over time to place limits on the size of the active core. Again, the black hole is not seen directly. Its presence is inferred through the discipline of measurement. As the observations accumulate, the object stops being merely a bright point and becomes a physical problem with a likely answer. The energy is too concentrated for ordinary starlight. The distance is too great for the brightness to be modest. The spectrum shows gas moving under strong forces. The compactness implied by variability points away from a whole galaxy shining evenly and toward a central engine. From this stage onward, the point in the sky is understood as the visible sign of an active galactic center, where matter is gathering and radiating near a supermassive black hole. Yet at this precise stage of the inward path, the most important fact remains visual and observational. The giant black hole does not arrive in astronomy as a giant black shape. It arrives as light arranged in a remarkable way. It appears first as a measured brightness at a fixed location, ancient and concentrated, separated from human observers by more than 10 billion years of travel. The eye sees a point, the instrument sees patterns. The analysis begins to reveal an object of extraordinary power hidden inside that narrow beam. This narrowing from cosmic distance to a single source in the sky is a quiet but necessary step. Before the quasar can be described, before the host galaxy can be considered, before the gas and the disk and the horizon can be approached, The object must first exist as an entry in observation. It must be found, distinguished, revisited, and confirmed. In that way, one of the largest known black holes begins not with darkness, but with a precise place in the sky and with light that refuses to behave like ordinary starlight. The point of light in the sky is now understood as a quasar, and this marks the next inward region of the subject. A quasar is the bright central part of a distant galaxy in an active state, where matter falls toward a supermassive black hole and releases large amounts of energy before it disappears from view. The word itself refers to appearance before explanation. It names something that first seems almost star-like, yet proves to be far more powerful and far more distant than any normal star. In the case of an object linked to one of the largest known black holes, the quasar is not a minor glow around the center. It is the dominant visible fact. It is the outward face of an extreme process taking place in a compact region. The brightness of a quasar can exceed the combined starlight of its host galaxy. This is one of the reasons the source appears so striking from across the depth of space. A normal galaxy shines because of hundreds of billions of stars spread across a vast structure. A quasar shines because gravitational energy is being converted into radiation in a much smaller central region. Gravity draws matter inward. As the matter moves and compresses, it heats. As it heats, it radiates. The process is efficient in a way that ordinary stellar burning is not. Nuclear fusion in stars releases part of the energy stored in matter, accretion, meaning the falling and gathering of matter under gravity can release an even larger fraction of mass energy before the material crosses the final boundary near the black hole. This central brightness is not a smooth lantern burning in silence. It is the visible result of gas, dust, and plasma moving under intense gravitational control. Plasma is matter so hot that electrons are no longer bound tightly to atomic nuclei. In the quasar environment, much of the gas is in this heated state. The light that emerges is spread across many wavelengths. Some of it is visible, some is ultraviolet, some is X-ray radiation from especially energetic regions. Together, this broad emission gives the quasar its great power and makes it observable over enormous distances. A quasar is therefore not the black hole itself. This distinction matters. The black hole remains dark in the sense that no light escapes from within the event horizon. The quasar is the surrounding activity made bright by falling matter. It is a luminous consequence of gravity rather than an exposed view of the hidden object. In ordinary language, the black hole is often treated as the whole phenomenon, but in observational astronomy the quasar is the visible engine around it. The inward path passes first through this zone of radiance before it can approach the deeper and darker center. In very distant quasars, this active state often appears more intense than what is seen in many nearby galaxies today. Observations indicate that the earlier universe contains many bright active galactic centers, suggesting that large supplies of gas are more commonly available to feed them. The quasar phase is not thought to last forever. It depends on continued inflow. When fuel decreases, the brightness can fall, leaving behind a quieter galactic center. In that sense, a quasar is understood as a period in the life of a galaxy rather than a permanent class of object. Some galaxies may pass through such a phase and later grow calm. The visual impression of a quasar is simple, but the physical meaning is layered. A brilliant point marks the place where gravity, motion, heat, and radiation interact at high intensity. The energy does not come from the black hole swallowing matter in some direct visible act. It comes mainly from the stages before swallowing. While matter is still outside the horizon and able to radiate, The closer matter moves inward, the more gravitational energy can be released. Because of this, a relatively small region can outshine an entire galaxy. This brightness also carries information. The spectrum of a quasar shows strong emission features from gas that is heated and stirred by the central engine. Some of the light is continuous, produced across a broad range of wavelengths by hot matter. Some appears in distinct lines linked to particular atoms and ions. An ion is an atom that has lost or gained electrons. These spectral features help reveal temperature, density, motion, and composition in the active environment. They are not decorative details. They are the main evidence through which the quasar is physically understood. At this scale, the central region is still too compact and too distant to resolve into ordinary shapes in most cases. The quasar does not yet spread into a visible disk or layered shell in the image. Its structure is reconstructed from brightness, spectral pattern, and variation over time. Even so, astronomy can say with confidence that the source is powered by matter gathering around a supermassive black hole. This model explains the luminosity, the compactness, and the observed changes in output better than older alternatives. It remains the accepted framework because it fits many lines of evidence at once. In the case of the most massive known candidates, the quasar becomes especially important because it is the means through which the black hole announces its scale. A black hole without feeding matter may remain difficult to study at great distance. A black hole in an active quasar state becomes visible across the cosmos. The brightness acts almost like a beacon, not because the black hole emits light, but because the surrounding matter is driven into a luminous condition by the depth of the gravitational well. The more massive the central object, the larger the region over which gravity can control high-speed motion, though brightness also depends on how much matter is arriving and how steadily it is supplied. There are limits to certainty here. Observations indicate that the quasar is powered by accretion onto a supermassive black hole, and this is strongly supported by data across many systems. At the same time, some details of the inner structure, especially in the most distant and extreme cases, remain less directly constrained. The exact geometry of emitting regions, the thickness of some flows, and the role of magnetic fields in shaping motion are active areas of study. These uncertainties do not overturn the general picture. They simply show that the luminous center, though well established in broad form, still contains fine structures that are difficult to isolate from afar. The quasar region is therefore the first truly bright interior zone of the story. It replaces the simple point of light with a physical environment powered by infell, heating, and radiation. It explains why a hidden object can become one of the brightest known sources in the distant sky. It reveals that the path inward does not begin in darkness, but in glare. Around the largest black holes, the surrounding activity becomes so radiant that it can cross billions of years of space and still arrive strong enough to be measured in detail. Within this region, the giant black hole is present as cause rather than image. The quasar is its visible atmosphere of energy, formed by matter still outside the final boundary and still capable of shedding light. The source that once seemed star-like is now understood as a galactic core in a state of intense feeding. Its brilliance marks the beginning of the inner descent, where radiation speaks first, and where the hidden mass at the center is approached by following the light it does not itself produce. Around the quasar, beyond the blinding center that dominates observation, there is a host galaxy. It is the largest stellar system in which the active core resides, the broad city of stars, gas, dust, and dark matter that contains the black hole within its central region. Yet in the case of an exceptionally bright quasar linked to one of the most massive known black holes, this galaxy does not present itself easily. The central light is so strong that much of the surrounding structure becomes difficult to isolate. The host exists with certainty in the general sense, because quasars are understood to be active galactic centers, but its detailed appearance may remain partly hidden behind the central brilliance. This imbalance between core and surroundings is one of the striking features of distant quasars. In a nearby quiet galaxy, starlight defines the visible form. Spiral arms may curve outward, or a smooth elliptical shape may fill the frame. The center may be brighter, but the galaxy as a whole remains the dominant structure in the image. In a powerful quasar, the relation is reversed. The active nucleus overwhelms the broader glow. The host becomes faint by comparison, as though a lantern has been placed at the center of a dim city, and the eye cannot fully adjust to both at once. Even so, the host galaxy is essential to understanding the black hole. The black hole does not float alone in intergalactic emptiness. It is rooted in a larger gravitational system. The stars of the galaxy move within a dark matter halo, a broad invisible structure inferred from gravitational effects. Gas circulates, cools, collapses, and sometimes flows inward. Dust absorbs and re-emits light. The black hole belongs to this system as its central compact object, and the quasar phase depends on the galaxy's ability to deliver matter toward the center. Without the host, there is no long-lived supply. Without the larger galaxy, the central engine cannot maintain its brightness for extended periods. In the nearby universe, observations show that many large galaxies contain central black holes whose masses are related in some broad way to properties of the surrounding stellar bulge. The bulge is the dense central concentration of stars in a galaxy. This relation suggests that galaxy growth and black hole growth are linked over long periods. The exact nature of that link remains an area of study, but the broad connection is well supported in the most extreme quasars. This raises an important question. If the black hole is so enormous, what kind of host galaxy surrounds it, and how did both grow together through cosmic time? Observations provide partial answers, but not always a complete picture, especially at great distance where the nucleus is so bright. The host galaxy of a powerful distant quasar is likely massive, rich in stars, and embedded in a substantial dark matter halo. It may also contain large amounts of gas, particularly in the earlier universe when many galaxies are still actively assembling their structure. The exact visible shape may be difficult to determine. Some hosts may resemble giant elliptical systems, while others may still show signs of interactions, asymmetry, or incomplete settling, in very distant and luminous cases. Observations indicate that the host can be hard to separate from the core, and uncertainty remains about some fine structural details. The general conclusion is clear, though. A black hole of extraordinary mass is expected to live in an equally substantial galactic environment. The central glare affects not only ordinary imaging but also interpretation. When the nucleus outshines the galaxy, measurements of the host become more sensitive to instrument quality, wavelength choice, and image processing. Infrared observations can help because they may reduce the contrast between the central source and the older stellar population of the galaxy. Even then, the separation is difficult. At very large distances, the host occupies a tiny apparent size in the sky, and its light is faint after travelling for billions of years. What reaches the observer is a mixture of nuclear brilliance and subtler galactic background. Teasing one from the other requires patience and careful modelling. The host galaxy is not merely a stage behind the quasar, it is a participant in the active process. Stars form from its gas. Supernova explosions enrich that gas with heavier elements. Gravitational disturbances can move matter inward. Bars, tidal interactions, and galaxy mergers may disturb the usual balance of orbits and help drive material toward the center. Not every active galaxy requires dramatic collision, and steady internal processes can also feed a nucleus. But in the most luminous cases, the scale of the required inflow suggests that major disturbances may sometimes play an important role. Observations support both merger-driven and non-merger pathways in different systems. It remains uncertain which path dominates for every ultramassive black hole. Because the host is partly hidden, the imagination may be tempted to treat the quasar as though it exists alone, as a kind of freestanding beacon in darkness. The actual picture is quieter and more physical. The light rises from the center of a galaxy that extends far beyond the compact engine. There are stars spread through wide regions, old stellar populations in bulk, perhaps younger clusters in certain zones, gas clouds moving through the interstellar medium, and a dark matter halo holding the larger structure together. The black hole is central, but it is still one part of a layered system. In this region of the inward path, scale remains important. The host galaxy may be tens or even hundreds of thousands of light-year across, while the active nucleus occupies a far smaller zone at the center, yet the brightness of that central zone dominates what can be seen. This is a lessening contrast. Physical size and visual dominance are not the same. A galaxy can be vast, and still disappear behind the power of a compact accreting core when viewed across immense distance. The host is larger, but the quasar is louder in light. The hidden nature of the host also leaves room for uncertainty that astronomy states plainly. Observations indicate a galactic environment massive enough to support an extreme central black hole. But it remains difficult in many cases to reconstruct the host in full detail. The brightness of the nucleus, the distance of the source, and the finite resolution of the instruments all limit certainty. This uncertainty does not weaken the overall understanding. It simply marks the boundary between what is securely inferred and what is still being refined through better observation. Seen from this layer, the black hole's surrounding world becomes broader than the quasar but dimmer in expression. It is the galaxy that carries the long history of star formation, chemical enrichment, gravitational assembly, and matter transport. It holds the reservoirs that can ultimately feed the core. It also conceals part of itself behind the very brilliance it helps sustain. The host is therefore both foundation and shadow. A vast system whose presence is necessary even when its details are hard to see. The inward path now rests in this hidden city of stars around the radiant nucleus. The black hole remains at the center, but the galaxy around it is no longer just an assumption. It is the larger body in which the whole process is rooted, a substantial structure partly veiled by its own central light, holding in quiet extension the materials and history that make the bright core possible. Beyond the visible stars of the host galaxy, and outside the immediate brilliance of the quasar, there exists a more diffuse region composed of gas and tenuous matter. This region does not shine with the same intensity as the central core, yet it plays an essential role in the long-term behavior of the system. It forms a wide reservoir from which material can gradually move inward over extended periods of time. In this outer domain, the matter is spread thinly across large distances, often existing in a state that is difficult to detect directly. Its presence is revealed through subtle absorption features in the light of the quasar and through faint emission at certain wavelengths. This gas is not uniform. It varies in density, temperature, and motion. Some regions are cooler and denser, capable of forming clouds that may eventually collapse under gravity. Other regions are warmer and more diffuse, shaped by the combined influence of radiation, past stellar activity, and the gravitational pull of the galaxy as a whole. The gas moves slowly compared to the rapid motions near the center, but its gradual drift is significant over long timescales. It forms the outermost supply chain for the central engine. In many galaxies, this extended gas exists as part of a halo. A halo is a roughly spherical region surrounding the main visible structure, containing both dark matter and ordinary gas. The dark matter cannot be seen directly, but its gravitational influence helps hold the galaxy together. The ordinary gas, though faint, can be studied through its interaction with light. When the light from the quasar passes through this gas, certain wavelengths are absorbed, leaving narrow signatures in the spectrum. These absorption lines provide information about the composition and motion of the intervening material. In the early universe, when the observed light from this system first begins its journey, such halos are often richer in gas than those seen in many nearby galaxies today. Observations indicate that galaxies at that time are still actively gathering matter from their surroundings. Filaments of gas connect galaxies across large distances, forming part of the cosmic web. Through these filaments, material can flow toward galaxies, adding to their mass and sustaining internal processes. The black hole at the center is therefore indirectly linked to structures far beyond the immediate galaxy, through pathways that guide matter inward over vast spans of space. The gas in these outer regions does not fall directly into the center in a simple path. It must lose energy and angular momentum, meaning it must shed some of its motion around the galaxy in order to move inward. This process is slow and often involves many stages: collisions between gas clouds, interactions with gravitational disturbances, and cooling processes all contribute to the gradual inward drift. The gas may first settle into the broader disk or bulge of the galaxy before moving further inward toward the central region. Temperature plays a quiet but important role. Gas that is too hot tends to resist collapse because its internal motion counters gravity. Gas that cools can condense more easily, forming denser structures that are more likely to move inward. Cooling occurs through radiation, as atoms and ions emit energy and allow the gas to lose heat. In the extended halo, cooling times can be long, but over millions of years. These processes shape the distribution of matter and influence how much material becomes available for deeper inflow. The outer gas reservoir is also affected by feedback from the central quasar. The intense radiation and energetic outflows from the active nucleus can push against surrounding material, heating it or driving it outward. This creates a balance that is not always steady. In some periods, inflow may dominate, feeding the black hole and sustaining the quasar. In other periods, outflow may limit the supply by removing or heating the gas. Observations indicate that both inflow and outflow occur, but the exact balance in any single system remains difficult to determine, especially at great distance. Because this region is faint, its structure is often reconstructed indirectly. Astronomers study the absorption lines imprinted on the quasar's light as it passes through intervening gas. Each line corresponds to a transition in a specific element or ion, such as hydrogen, carbon, or oxygen. The width and shift of these lines reveal motion and temperature. From many such measurements, a picture emerges of gas distributed in a halo, moving under gravity and influenced by the radiation from the center. The scale of this region is vast compared to the central engine. It can extend far beyond the visible boundary of the host galaxy, blending into the intergalactic medium. Yet its connection to the center is real, even if indirect. Over long periods, The slow inward movement of gas from these outer regions contributes to the supply that eventually reaches the quasar. Without such a reservoir, the central brightness could not be sustained for extended durations. In this outer layer, the environment is quiet compared to the intense activity closer to the center. Motions are slower, temperatures are more moderate, and radiation is less extreme. The processes unfold over long timescales, measured in millions of years. The gas drifts, cools, and interacts in subtle ways. It does not announce itself with brilliance, yet it forms the beginning of the path that leads inward. The existence of this reservoir also emphasizes that the black hole's growth is not only a local process, it depends on conditions across the entire galaxy and even beyond it. Matter must be gathered, transported, and delivered through many stages before it can contribute to the central engine. Each stage leaves its mark on the system, shaping how efficiently material can move inward and how long the active phase can last. Observations indicate that such extended gas halos are common around galaxies, though their exact properties vary widely. In distant quasars, the combination of strong radiation and abundant gas creates a dynamic environment that is still being studied in detail. It remains uncertain how uniform these halos are and how they evolve over time, but their role as a supply region is widely accepted. This outer reservoir marks the transition from the broader galaxy to the more focused regions that lie closer to the center. It is the first step inward from the large-scale structure, a region where matter begins its slow journey toward the gravitational well. The black hole is still far away in this view, hidden behind many layers of motion and transformation. Yet the path toward it has begun, carried by faint gas drifting through the outer reaches of the host galaxy and beyond. From the wide gas reservoir around the galaxy, the inward path now reaches a region that lies much closer to the active center. This region is known through its light rather than through any direct image. It is called the broad line region because the spectral lines produced there appear widened, spread across a greater range of wavelengths than narrow lines from calmer gas farther out. A spectral line broadens when the emitting gas moves at very high speed. Some of the gas travels toward the observer, shifting its light slightly to shorter wavelengths. Some travels away, shifting it to longer wavelengths. When all of that light is gathered together, the line becomes wide. In this way, motion leaves its shape in the spectrum. The broadline region is one of the most useful zones in the study of distant quasars. It cannot usually be seen as a resolved structure, especially in systems that are so remote and so bright. Yet its presence is unmistakable in the light. The gas there moves under strong gravitational influence, much faster than gas in the wider host galaxy. The speeds are often thousands of kilometers per second. Such motion indicates that the gas lies in a deep gravitational well and at a relatively small distance from the central mass. The region therefore acts as a messenger from a hidden zone, carrying information outward in the form of broadened emission lines. This gas is illuminated by the central source. Radiation from the hot inner parts of the active nucleus strikes the surrounding material, excites atoms and ions, and causes them to emit light at characteristic wavelengths. Hydrogen, carbon, magnesium, and other elements contribute to these lines, depending on the conditions. The gas is not cold and still. It is heated, ionized, and stirred by intense radiation and gravity. The result is an environment that is both luminous and restless. Positioned between the wider galactic surroundings and the deeper accreting structure nearer the black hole. Because the region is defined through motion, it becomes a major tool for estimating black hole mass. The principle is quiet and powerful. Faster gas motion implies stronger gravity. If the approximate distance of the gas from the center can also be estimated, Then the central mass can be inferred. Astronomers use the width of the broad emission lines as one part of this calculation. They combine that with the brightness of the quasar, which helps estimate the size scale of the emitting region through empirical relationships built from better studied active galaxies. The result is not a simple direct weighing, but it is one of the main accepted methods for estimating the masses of distant supermassive black holes. This is how one of the largest known black holes enters scientific measurement. The broad-line region, though itself made of gas rather than of solid structure, becomes part of the evidence that the central mass is astonishingly large. Broad lines alone do not prove an exact value with perfect certainty. The method includes assumptions about geometry, about how the gas is distributed, and about how closely its motion reflects the black hole's gravity. Even so, the overall conclusion remains strong when multiple lines of evidence agree. The gas is moving too fast, and the quasar is too luminous for the central object to be modest in mass. The broad-line region is not thought to be a thin, neat shell. Its structure is likely complex. Some of the gas may orbit in flattened arrangements, some may move inward, some may move outward in winds driven by radiation pressure or magnetic effects. Radiation pressure is the push exerted by intense light on matter. In a powerful quasar, this push can be significant. Observations indicate that the broad-line region contains both ordered and disordered motion, and it remains uncertain exactly how much each contributes in every source. The region is best understood not as a single simple ring, but as a dynamic zone of fast-moving clouds or streams responding to gravity and illumination. Despite this complexity, the broad-line region marks an important narrowing of the inward journey. The gas here is much closer to the central engine than the halo gas and the larger host galaxy. It responds directly to the active nucleus, not only to the galaxy as a whole. The light emitted here is therefore more immediate in its connection to the black hole. The lines broaden because the gas is living under the influence of powerful gravity. The spectrum becomes a map of speed, and speed becomes a clue to mass. There is also an important timescale associated with this region. Because it is relatively compact compared with a full galaxy, it can respond to changes in the central radiation on shorter timescales. In some nearby active galaxies, astronomers observe the delay between changes in the central light and the later response of emission lines from surrounding gas. This technique is called reverberation mapping. A reverberation is an echo-like response. The method helps estimate the size of the broad-line region by measuring light travel delays within the system itself. For the most distant and extreme quasars, such detailed measurements are more difficult, but the principle established in nearer cases supports the broader framework used at large distances. The gas in this region is dense compared with more extended galactic gas, though still thin by everyday standards. It exists in an environment where ionizing radiation is strong, where orbital speeds are high, and where the distinction between cloud, stream, and wind may blur. The temperature and ionization state vary across the region. Some lines arise in more highly ionized gas, some in less highly ionized material. These differences suggest internal layering or varying exposure to the central source, though the exact arrangement is still studied. What remains clear is that the broad-line region is not random decoration around a quasar. It is one of the main physical intermediaries between the visible radiation field and the hidden central mass. In the case of an ultramassive black hole, the broad-line region also expresses scale through its size. A more luminous quasar generally supports a broader emitting zone at greater distance from the center than a weaker active nucleus does. Yet the gas still moves quickly because the gravitational field remains so strong. This combination of large radius and high speed points toward a central object of enormous mass. The black hole itself is still unseen, but the surrounding gas behaves as though it is circling an immense invisible anchor. Uncertainty remains part of the scientific picture. Observations indicate that the broadline region is real and physically important, but it remains uncertain exactly how its geometry varies from source to source. Some mass estimates may shift depending on orientation, gas distribution, or additional forces beyond simple orbital motion. These uncertainties matter, and they are stated plainly in research. They do not erase the broader conclusion that some quasars host black holes of extreme scale. They only remind that the route to such knowledge passes through inference rather than direct inspection. At this inward layer, the story is carried by moving gas and widened light. The broad line region forms a luminous envelope of speed around the deeper central engine. It is not yet the accretion disk, and it is not the black hole, but it lies close enough to feel the central gravity strongly, and to reveal that hidden gravity in measurable form. The distant source that first appears as a point in the sky now becomes a place where gas races through intense radiation, and where the width of spectral lines quietly announces the presence of a mass large enough to seem almost impossible. The inward path now enters the accretion disk, beginning with its outer regions. An accretion disk is a rotating structure of gas and plasma that forms when matter spirals inward toward a massive central object, instead of falling directly inward in a straight line. The material spreads into a flattened disk because it carries angular momentum, meaning it already has motion around the center. As the gas continues its inward journey, it must gradually lose some of this motion. The outer disk represents the stage where this process is still relatively gentle, where rotation is orderly, and where conditions, though energetic, are not yet at their most extreme. In this outer region, matter orbits the central black hole along paths that are broadly circular. The gravitational pull is strong, but not yet overwhelming compared to the inner zones. Gas clouds entering this region may come from the broader galaxy, or from the inner edges of the gas reservoir. As they settle into orbit, collisions and interactions between particles begin to shape the disk. These interactions cause friction, not in the everyday sense of solid surfaces rubbing, but through repeated small exchanges of energy and momentum between particles. This friction allows the gas to lose energy while maintaining its overall rotation, causing it to move slowly inward over time. Temperature in the outer disk is elevated compared with the wider galaxy, but still lower than in the regions closer to the center. The gas emits light, often in visible and ultraviolet wavelengths, though the intensity here is less than in the inner disk. The emission arises because the gas is heated by compression and by the gradual release of gravitational energy. Each orbit brings slight changes. Each interaction spreads energy through the disk. Over time, a steady pattern emerges, where material drifts inward while radiating energy outward. The outer disk is not perfectly smooth. It may contain variations in density, regions where gas is slightly thicker or thinner, and zones where instabilities develop. These instabilities can lead to waves or spiral patterns within the disk, somewhat like ripples in a fluid. Such patterns help redistribute angular momentum, allowing some material to move inward while other material moves outward. This exchange is essential. Without it, the gas would remain in stable orbits and would not approach the central black hole. The disk exists because of this slow and continuous rearrangement of motion. Radiation from the central regions also reaches the outer disk. This radiation can heat the gas further, altering its temperature and ionization state. Ionization means that atoms lose electrons under the influence of energy, changing how they interact with light. The balance between heating and cooling in the outer disk determines how bright it becomes and what wavelengths it emits. Cooling occurs when the gas radiates energy away, allowing it to settle into a relatively stable structure. Heating occurs through friction and through incoming radiation. The interplay between these processes shapes the disk's outer layers. The scale of the outer accretion disk can be large compared with the central black hole itself. Even though the black hole holds most of the mass in the immediate region, the disk extends outward across a much wider area. In the case of an ultramassive black hole, this outer disk can span distances that would dwarf the size of planetary systems, yet it remains a small structure compared with the host galaxy as a whole. This layering of scale continues the pattern seen throughout the inward path, where each step reveals a new level of structure within a larger one. Motion in the outer disk is fast by everyday standards, but still slower than in the inner regions. Gas completes orbits over timescales that depend on its distance from the center. Farther out, the orbital period is longer. Closer in, it becomes shorter. This gradient in orbital speed contributes to the internal friction of the disk. Adjacent rings of gas move at slightly different speeds, leading to shear, a difference in motion that promotes mixing and energy exchange. Shear is one of the key drivers that allows the disk to evolve rather than remain static. The outer disk also serves as a transition zone. Material entering from the broader galaxy begins to align with the disk's rotation. Random motions are gradually organized into a coherent pattern of orbiting flow. At the same time, material moving inward begins to encounter conditions that will become more intense. The outer disk is therefore both an entry point and a preparation stage. It does not yet display the highest temperatures or the most extreme speeds, but it establishes the structure that will carry matter deeper toward the black hole. Observations of distant quasars do not usually resolve the outer disk directly. Instead, its presence is inferred from models that explain the observed light. The distribution of brightness across different wavelengths suggests a range of temperatures within the disk, with cooler regions farther out and hotter regions closer in. This temperature gradient is consistent with the idea of an extended disk, where energy is released gradually as matter moves inward. While details of thickness, turbulence, and exact geometry may vary, the general picture of a rotating accretion disk is widely accepted. There remain uncertainties in how precisely the outer disk behaves in the most extreme systems. The influence of magnetic fields, for example, may play a role in transferring angular momentum more efficiently than simple particle interactions alone. Magnetic fields can connect different parts of the disk, allowing energy and motion to be redistributed in complex ways. Observations indicate that such processes are important, but the exact details are still being explored. These uncertainties do not remove the central idea. They refine it, adding depth to the understanding of how matter moves inward. In this region, the journey toward the black hole is steady rather than dramatic. The gas orbits, interacts, cools, and gradually shifts its position. Light is produced, but not yet at the most intense levels. The disk forms a broad, rotating platform that channels material inward. It is neither as diffuse as the outer halo nor as extreme as the inner zones. It is an intermediate layer shaped by gravity and motion, where the long process of accretion becomes organized and sustained. The black hole itself remains unseen, still deeper within the structure, yet its presence is felt through the very existence of the disk. Without the central gravity, there would be no inward pull to organize the flow. Without the need to shed angular momentum, there would be no disk at all. The outer accretion disk is therefore both a response to the black hole and a pathway toward it, a wide, rotating region where matter begins its final approach under conditions that are increasingly controlled by the unseen mass at the center. From the outer disk, where matter settles into broad rotation and begins its long inward drift. The path now reaches the middle regions of the accretion disk. Here the structure becomes brighter, hotter, and more active. The motion remains organized in the sense that the gas still circles the black hole in a flattened form, yet the physical conditions are no longer gentle. The inward flow has advanced far enough that gravity releases energy at a greater rate. Friction within the disk grows more important. Compression increases, the radiation from the disk strengthens. This middle region is where the slow preparation of the outer disk becomes a more intense conversion of motion and gravity into light. The gas in this part of the disk moves faster than gas farther out. The closer matter comes to the center, the greater the orbital speed required to remain in orbit. Each inner ring therefore overtakes the next outer ring, and the difference in speed between neighboring layers becomes stronger. This difference is called shear. In the middle disk, shear is a persistent source of internal stress. It stirs the material, helps transport angular momentum outward, and allows matter to continue its gradual inward motion. Without this transfer, the gas would remain trapped in stable orbits. With it, the disk can continue to evolve. As the matter moves inward, gravitational energy is released more efficiently. This does not happen in a single burst. It unfolds continuously, as gas shifts from one orbit to another and settles deeper into the gravitational well. The energy appears mainly as heat. The temperature rises, and the disk begins to radiate more strongly at shorter wavelengths, while the outer disk contributes visible and ultraviolet light. The middle disk strengthens the ultraviolet emission and pushes the spectrum toward greater intensity. In a powerful quasar, this bright middle zone becomes part of the broad luminous body that allows the active nucleus to outshine its host galaxy. The material here is plasma, heated enough that atoms are often stripped of some or all of their electrons. This ionized state changes how the gas responds to radiation and magnetic fields. The particles are no longer behaving like the cooler gas clouds of the outer halo or the wider galaxy. They move in a hotter, more electrically active environment. Magnetic fields can thread through the plasma and help link one region of the disk to another. These fields are thought to play a major role in the transport of angular momentum. Observations and theory both indicate that simple microscopic friction alone is not enough to explain the efficiency of the inward flow. The disk appears to behave as a turbulent magnetized fluid, with small disturbances amplified into broader patterns of mixing and stress. Turbulence in this context means irregular motion superimposed on the overall orbital flow. It does not erase the disk structure, but it makes the local motion more complex. Small eddies, fluctuations in density, and changing magnetic fields all contribute to a restless internal state. This restlessness helps the disk function. It spreads energy, redistributes motion, and keeps matter moving inward at a measurable rate. The middle disk is therefore not a calm sheet of glowing material. It is a dynamic, heated region whose apparent steadiness hides continuous internal activity. The thickness of the disk may also change in this zone. In simpler descriptions, accretion disks are often imagined as very thin structures, and in many cases this is a useful approximation. But in luminous quasars, especially those surrounding extremely massive black holes, radiation pressure can become important. Radiation pressure is the outward push exerted by light on matter. In the middle disk, where the brightness is high, this pressure may help support the disk vertically, giving it more thickness than a purely cold, thin disk would have. The exact shape depends on the balance between gravity pulling inward, pressure pushing outward, and cooling carrying energy away. Observations support the general picture of a hot, radiating disk, though the precise thickness and internal geometry remain uncertain in some extreme sources. Cooling remains essential even in this hotter zone. As the gas heats, it radiates energy away. If it could not cool, the structure would swell and change character more dramatically. The balance between heating and cooling gives the middle disk a quasi-steady form, meaning it remains broadly stable even while matter flows through it. New material enters from farther out, energy is released, light escapes, and matter continues inward. The disk is therefore not a fixed object but a process held in shape by continuous motion. This middle region also contributes to the overall spectral character of the quasar. Different distances from the center correspond to different temperatures, so each annulus of the disk radiates somewhat differently. Together, these annuli form a broad distribution of light. The middle disk helps fill the spectrum between the cooler outer parts and the still hotter inner parts. It is a major source of the intense ultraviolet output that characterizes many active galactic nuclei. That light then travels outward and illuminates other regions, including the broad-line gas described earlier. In this way, the middle disk not only radiates directly, but also helps shape the wider luminous environment. Scale continues to matter here. Around an ultramassive black hole, the physical size of each disk zone can be enormous compared with ordinary human reference points. Distances within the disk may exceed those familiar from planetary systems, yet the structure remains tiny compared with the host galaxy. This layered perspective remains important for keeping the proportions clear. The middle disk is a local region in the life of the galaxy, but within that local region it's already a vast and highly energetic world of orbiting plasma. The timescales within the middle disk are shorter than in the outer disk. Because the orbits are smaller, matter circles the center more quickly. Changes in brightness originating from this zone may therefore occur on shorter timescales than changes from farther out. Though in distant quasars, these patterns are not always easy to isolate. Even so, the principle remains. Closer regions evolve more quickly. The deeper the descent into the gravitational well, the faster the natural rhythm of motion becomes. There are still uncertainties in the fine details, the exact role of magnetic instabilities, the degree of turbulence, and the interaction between radiation pressure and disk thickness are active subjects of study. Observations indicate that these effects matter, but the most distant and brightest quasars do not always allow a clean separation of one process from another. The broad framework remains secure. A heated, rotating, luminous middle disk exists between the cooler outer flow and the deeper inner zone, and it converts gravitational energy into radiation with great efficiency. In this region, the journey inward becomes visibly more intense. The disk brightens, the plasma grows hotter, motion tightens. Energy that once remained stored in orbit is gradually released into heat and light. The black hole is still deeper inside, not yet reached. But its pull now shapes the character of the gas more strongly than before. The middle accretion disk is therefore a region of transformation, where the ordered rotation inherited from larger scales is refined into a brighter, faster and more energetic flow, preparing matter for the even more extreme conditions that lie nearer the center. From the hotter middle disk, the inward path now reaches the inner accretion disk, where gravity, speed, and heat intensify together. In this region, matter still remains outside the event horizon, still capable of emitting light, but it now moves under conditions far more severe than those in the outer zones. The black hole's pull governs nearly every aspect of the flow. Orbits tighten, velocities rise to a substantial fraction of the speed of light. The gas becomes hotter. thinner in some directions, and more deeply affected by both radiation and relativity. Relativity here means the physical rules that become especially important in strong gravity and at very high speed. In the inner disk, these rules are no longer small corrections, they are part of the structure itself. The basic shape of the disk remains flattened, but its behavior changes. Farther out, matter can drift inward through many gradual steps while remaining on broadly stable orbits. In the inner disk, the room for stability narrows. Each orbit exists deeper within the curved geometry of spacetime around the black hole. Spacetime is the joined framework of space and time described by modern gravity. Near a very massive object, that framework is curved in a way that changes how motion unfolds. The gas does not simply circle in ordinary space. It follows paths shaped by the deep gravitational well. These paths can remain stable only down to a certain limit. Inside that limit, matter can no longer maintain a lasting circular orbit and begins a more direct plunge inward. This limiting boundary is called the innermost stable circular orbit. It marks the inner edge of the region where matter can circle in a relatively sustained way before the final descent begins. The exact location of this boundary depends on the black hole's mass and on whether it is rotating. Rotation matters because a spinning black hole changes the surrounding spacetime, allowing stable orbits to exist closer in for matter, moving in the same direction as the spin. Observations indicate that many supermassive black holes do rotate, but for the most distant and extreme systems, it often remains uncertain exactly how fast a given black hole is spinning. Even with that uncertainty, the concept remains important. The inner disk extends down toward this boundary, and the conditions become increasingly intense as it approaches. Temperature rises sharply in this zone. The gas is heated by friction, compression, magnetic effects, and the rapid release of gravitational energy. Much of the emission from the inner disk moves into the ultraviolet and may contribute to even more energetic bands through interaction with hotter regions above the disk. The plasma here is highly ionized and dynamic. Density, pressure, and radiation all interact in a narrow volume where the flow is both bright and unstable. The light produced in this inner region contributes strongly to the total power of the quasar. It is one of the last bright stages of matter before it passes into darkness. Speed defines this zone as much as temperature does. The gas orbits so rapidly that ordinary comparison begins to fail. Instead of thinking in familiar mechanical terms, it becomes more accurate to imagine motion pressed close to its natural limit, where time, direction, and the appearance of light are all altered by velocity and gravity. Parts of the disk moving toward the observer appear brighter because their emitted light is concentrated by motion, while parts moving away appear dimmer. This effect, known as relativistic beaming, changes the apparent brightness pattern of the inner disk. Gravity itself also alters the light. Photons climbing outward from the deep gravitational field lose energy, causing their wavelengths to stretch. This is called gravitational redshift. The inner disk is therefore not only a place of intense light production, it is also a place where light is reshaped before it escapes. Magnetic fields remain important and may become even more influential here. In the inner disk, magnetized turbulence continues to transport angular momentum outward, allowing matter to move inward. At the same time, magnetic activity may lift some energy above the disk and contribute to the formation of hotter regions or outflows. The exact details remain uncertain and depend on simulations, indirect evidence, and comparison across many active galaxies. Still, observations and theory together indicate that the inner disk is not controlled by gravity alone. It is a magnetized and radiating flow in which several forms of stress act at once. The thickness of the disk in this inner zone may differ from that of a perfectly thin classical model. In very luminous systems, radiation pressure can support the disk more strongly, altering its vertical structure. In some models, the flow may puff up slightly or change character where the brightness approaches a limiting level for stable accretion. That limiting level is often discussed in terms of the Eddington limit, which is the point where outward radiation pressure balances inward gravity for ionized gas under simple conditions. A quasar can approach this limit or in some cases exceed it locally for a time, though the exact interpretation depends on geometry and flow structure. For an ultramassive black hole, the enormous mass allows very high luminosity before this balance becomes restrictive. Yet the inner disk still lives in negotiation between inward pull and outward radiative push. Time also behaves differently in this region. To a distant observer, clocks closer to the black hole appear to run more slowly because of strong gravity. This effect, called gravitational time dilation, does not stop the local motion of the gas, but it changes how events are related between the inner disk and the far observer. Light arriving from this depth carries the imprint of that difference. In the scientific picture, the inner disk is therefore not just deeper in space. It is deeper in gravitational time. This does not make the region mysterious in a vague sense. It makes it physically distinct in a precise way. The inner accretion disk is also where the visual simplicity of a flat rotating structure begins to break down under extreme conditions. The gas remains arranged in a disk overall, but the combination of strong gravity, rapid motion, high radiation, and magnetic stress means that local behavior can be irregular. Small changes in inflow, density, or magnetic configuration may alter how efficiently the region emits energy. Variability seen in active galactic nuclei often has contributions from these deeper layers, though in very distant quasars, the exact origin of each change is not always easy to isolate. Observations indicate that the inner disk can fluctuate while still maintaining a broadly stable average structure over longer periods. There is an important quietness to this region despite all the violence implied by the physics. The gas does not explode in every direction. It does not abandon order completely. It continues to circle, emit, and drift inward according to the constraints of gravity. The inner disk is extreme, but it is also disciplined. Its brightness is the result of matter obeying physical laws in a very deep gravitational field. That obedience is what makes the quasar comprehensible. Even at the edge of stable motion, the flow still follows a pattern that observation can study. Uncertainty remains in several details. It remains uncertain how thick the innermost flow becomes in the brightest quasars, how magnetic fields are arranged at the smallest scales, and exactly how the black hole's spin modifies the deepest visible orbits in every extreme source. These questions matter because they affect the final efficiency of light production and the shape of the escaping spectrum. Yet the broader picture is secure. The inner disk is a region of very high speed, strong gravity, and intense radiation, located just outside the point where long-lived orbits end. At this stage of the inward path, matter has nearly completed its visible journey. It still shines, but it does so while circling on borrowed time. The black hole's gravity now dominates the structure so completely that only a narrow range of motion remains possible. The inner accretion disk is therefore the last great ring of light, a bright boundary zone where the largest known black holes reveal their strength most clearly before the final plunge carries matter beyond all further emission. From the inner disk, where matter still follows the last stable patterns of orbit, attention now moves to the radiation nearest the center, This region is not defined by a solid surface or a separate shell of matter. It is defined by energy, by the most intense light produced in the active nucleus before the final loss of visibility. The disk remains part of the picture, but the focus here is on the radiation field itself and on the especially hot regions above and around the inner disk that shape the quasar's strongest emission. In this narrow domain, light becomes the main physical sign of depth. The closer the process lies to the black hole, the more energetic the escaping radiation tends to be. The bright output of a quasar does not emerge from one temperature alone. Different parts of the accretion flow radiate at different energies, and the combined result forms a broad spectrum. The outer disk contributes cooler light. The middle and inner disk contribute hotter ultraviolet light. Near the center, there is also evidence for an even hotter region above the disk, often called the corona. In this context, a corona is a region of very hot, tenuous plasma located above and below the disk, not unlike the use of the same word for the hot outer atmosphere of a star, though the physical setting is different. The plasma there is so energetic that it can affect lower energy photons passing through it and push them to much higher energies. This process helps explain the strong X-ray emission observed from active galactic nuclei. Photons rising from the hot inner disk can encounter fast electrons in the corona. When this happens, the photons can gain energy through repeated scattering. Scattering means the photons change direction and energy through interaction with particles. In the corona, this can transform ultraviolet light into X-rays. The result is a compact source of very energetic radiation close to the black hole. The corona is not directly seen as a separate shape in distant quasars, but its presence is inferred from the spectrum and from the way certain features in the X-ray light behave. The radiation nearest the center therefore contains two linked parts. One part comes from the hot inner disk itself, the other part comes from the reprocessing and boosting of that light in the corona. Together they create a concentrated field of emission that illuminates nearby gas, contributes to the total output of the quasar, and carries some of the clearest signatures of strong gravity. The X-rays in particular are important because they can originate very close to the black hole, closer in some cases than much of the ultraviolet emitting disk. They are therefore among the most direct observable messengers from the central engine. This region is intense, but it is not simple. Radiation does not move outward untouched. Some of it escapes directly to distant observers. Some of it strikes the disk and is reflected or re-emitted. Some of it interacts with gas farther out, ionizing atoms and helping power the emission lines seen from other regions. Some may be bent by gravity itself, near a black hole. Light does not travel along the straight paths familiar from weak gravitational settings. The curvature of space-time deflects its course. This light bending can change how much radiation reaches the observer and how much returns to strike the disk. In the deepest regions, the observed brightness is therefore shaped not only by how much light is produced, but also by how gravity guides that light on its way outward. The spectrum of radiation near the center often includes features that reveal this environment. One of the most studied is the ion emission feature seen in X-rays in many active galactic nuclei. Ion atoms in the disk can emit characteristic X-ray photons when illuminated by the corona. Near the black hole, however, the combination of rapid motion, gravitational redshift, and light bending distorts this feature. Instead of appearing narrow and simple, it can appear broadened and skewed. Observations of such features in some systems provide evidence that the emission is coming from very close to the black hole. In the most distant and extreme quasars, the signal may be harder to isolate, but the physical principle remains part of the accepted picture of central radiation. The corona itself remains one of the less directly constrained parts of the system. Observations indicate that it exists and that it plays a major role in producing high-energy emission, but its exact geometry remains uncertain. It may form as a compact source near the axis above the black hole. It may be more extended across the inner disk. It may vary in height, size, and structure over time. Magnetic fields are thought to be important in heating the corona, perhaps through reconnection, where magnetic field lines change configuration and release energy into the plasma. This process is well established in plasma physics in general, though the exact arrangement near a quasar's center remains difficult to map in detail. The radiation field near the center also participates in a balance of force. Light carries momentum, and intense light can push on matter. In the inner regions of a luminous quasar, this radiative push can alter the flow of gas, support layers of plasma, and help launch winds from the disk surface. The energy escaping from near the black hole is therefore not passive. It acts back on the surrounding material. Yet even this strong radiation does not stop accretion entirely. The flow continues because gravity remains dominant overall, and because the geometry of the disk allows matter to keep moving inward, while much of the radiation escapes vertically or through less obstructed paths. Variability is especially important in this region. Since the corona and the deepest visible disk are compact, their light can change on relatively short timescales compared with the outer parts of the system. In some active galaxies, astronomers observe changes in X-ray brightness that suggest a very small emitting region close to the black hole. These changes can also be echoed in reflected light from the disk after a short delay, giving clues to the geometry of the central engine. For the most distant quasars, such timing measurements are more difficult, but the same physical reasoning supports the picture of a compact high-energy source near the center. This radiation is also the most revealing and the most filtered. It reveals the central conditions because it originates so near the black hole. It is filtered because gravity, speed, scattering, reflection, and absorption all alter it before it escapes. What finally arrives at a telescope is not a pure original beam. It is a worked-over signal shaped by the deepest accessible region of the system. Reading that signal requires models and careful comparison across many wavelengths. When the models fit, they indicate a central engine of remarkable efficiency, able to transform in falling matter into light across the spectrum. For an ultramassive black hole, this central radiation can be enormous in total power, while still arising from a region small compared with the galaxy. That combination remains one of the defining features of a quasar. A narrow zone near the center becomes luminous enough to dominate a whole stellar system. The light carries the marks of extreme heat, dense gravity, and relativistic motion. It does not show the black hole directly, but it traces the last visible territory around it with unusual clarity. Uncertainty remains in the fine structure of the corona, in the exact pathways of energy transfer from magnetic fields to hot electrons, and in how the geometry of the central radiation field differs from one quasar to another. Observations indicate the general picture strongly, but some details remain open. Even with those uncertainties, the central meaning is clear. Near the black hole, light reaches its highest energies, and that energetic light becomes the most immediate outward sign of the hidden mass below. In this region, radiation itself becomes the landscape, a compact blaze above the final orbits, marking the closest visible approach to the center that observation can usually reach. Beyond the hot inner disk and the compact regions of highest radiation, the inward path reaches the event horizon. This is the boundary that defines the black hole in the strict physical sense. It is not a surface made of matter. It is not a wall, a shell, or a visible edge suspended in space. It is the limit beyond which no signal can return to the outside universe. Light emitted from within this boundary does not escape. Matter that crosses it no longer contributes directly to outward observation. For a distant observer, the event horizon marks the end of visible participation in the surrounding world. The name event horizon can be stated simply: an event is something that happens at a particular place and time. A horizon is a boundary beyond which something cannot be seen. In this case, the horizon is the boundary beyond which events cannot send information outward to distant observers. This definition makes the event horizon different from the apparent edges of ordinary objects. A planet has a visible surface because light reflects from it. A star has a photosphere, which is the layer from which most visible light escapes. The event horizon has no such luminous outer skin of its own. It is a boundary of causation, a limit set by gravity and the structure of space-time. Around an ultramassive black hole, the size associated with this horizon is enormous in human terms. For a non-rotating black hole, the radius of the horizon increases directly with mass. This means that the larger the black hole, the larger the region from which light cannot escape. In the case of one of the largest known black hole candidates, the diameter of this boundary would extend across a scale far greater than the orbit of Pluto around the Sun. Yet even this immense horizon remains tiny compared with the full host galaxy. The familiar pattern continues. The black hole is vast by local standards and small by galactic ones. The event horizon is often imagined as a place where matter is violently torn apart at the very boundary. But this is not always the best picture, especially for extremely massive black holes. Tidal force, which is the difference in gravitational pull between one part of an object and another, depends on both mass and distance from the center for very massive black holes. The horizon lies far enough from the center that these tidal differences at the horizon can be smaller than they are for much smaller black holes. This means the crossing of the horizon, in principle, need not correspond to a sudden local catastrophe for falling matter at that exact location. The horizon remains decisive for information and escape, but not necessarily dramatic in the local mechanical sense at the moment of crossing. To a distant observer, the appearance of matter near the horizon is shaped by relativity. Light emitted from gas falling inward becomes increasingly redshifted as it climbs out of the deep gravitational field. Redshift here means the stretching of wavelength toward the red end of the spectrum as energy is lost during escape. At the same time, the rate at which processes appear to unfold slows because of gravitational time dilation from far away. Matter seems to fade and slow as it approaches the horizon. It appears dimmer, redder, and increasingly delayed. This does not mean the matter actually stops in its own local frame. It continues inward and crosses the boundary in finite time by its own clock. The strange appearance belongs to the difference between local experience and distant observation. This distinction is one of the most important features of the event horizon. Locally, the falling matter does not encounter a marked material surface. Globally, the outside universe loses causal contact with anything that passes inward. Both statements are part of the accepted description in general relativity. The horizon is therefore subtle, it is real, but not in the same way as a solid edge. It changes what can be known and what can be influenced from outside, even though it is not directly seen as a separate luminous object. Rotation can modify the structure around the horizon. A spinning black hole drags nearby spacetime, an effect known as frame dragging. In such cases, the horizon is accompanied by an outer region called the ergosphere, where spacetime is carried around with a spin so strongly that no object can remain at rest relative to a distant observer. The ergosphere lies outside the horizon and still allows escape in principle, while the horizon remains the final no-return boundary. For distant extreme quasars, the exact spin of the central black hole often remains uncertain, so the precise shape and size of these regions cannot always be specified. Even so, the event horizon itself remains a core part of the picture, whether the black hole rotates slowly or rapidly. The horizon cannot be observed directly in the same way that surrounding gas can be observed. What astronomy studies is the behavior of matter and light just outside it, in nearby black holes, such as the one imaged by the Event Horizon Telescope in the galaxy M87. The surrounding light can reveal a dark central feature associated with the shadow cast by the black hole. For a distant quasar hosting an ultra-massive black hole, such direct imaging is far more difficult at present. The horizon remains inferred through the consistency of the theory and through the observed behavior of nearby matter. Observations indicate that matter flows inward toward a boundary from which no further light is received, and this matches the event horizon picture extremely well. The event horizon also marks the point at which the accretion process, as an observable radiative engine, comes to an end. Most of the light associated with the quasar is produced before matter crosses this boundary. The efficiency of accretion lies in what happens outside, where gas can still heat and radiate. Once across the horizon, the matter no longer contributes new outward light. In that sense, the horizon is the line between visible transformation and hidden continuation. Everything described in the disk, the corona, and the fast-moving gas belongs to the outside region where information still escapes. The horizon closes that region. It is important not to confuse the horizon with the center. The horizon is not the singular interior point often mentioned in simplified descriptions. It is the outer boundary of the black hole. The deeper interior, whatever exact form it takes under complete physics, lies further inward. At this stage of the inward journey, only the boundary itself is under examination. That boundary is already enough to define the black hole as an object of no return. It is already enough to separate observable processes from those hidden permanently from outside view. Uncertainty remains in how best to describe the horizon when quantum effects are considered. General relativity gives a clear classical picture of the event horizon, and this picture matches observations very well in the regimes accessible so far. At the same time, a complete union of gravity and quantum physics is not yet established. Because of that, it remains uncertain whether the deepest theoretical description of the horizon is exactly the same as the classical one in every respect. This uncertainty does not affect the practical astrophysical conclusion that black holes possess a boundary of no return consistent with the event horizon idea. At this inward layer, the visible universe reaches its last limit. Matter still glows outside. Light still carries news outward. Then the boundary is crossed, and no further report emerges. The event horizon is therefore not a dramatic wall of darkness, but a precise end to outside knowledge. A quiet dividing line in space-time where the largest known black holes finally become black in the full physical meaning of the word. From the event horizon as a boundary of no return, attention now settles on mass and physical size. These are the measures that make an ultramassive black hole seem almost impossible at first encounter. Mass describes how much matter and energy are concentrated into the object and how strongly it curves space-time around itself. Size, in the simplest outward sense, refers to the scale of the horizon associated with that mass. Yet with a black hole, size cannot be understood in the same way as the size of a star, a planet, or a cloud. There is no ordinary surface, no visible body filled with layered material that can be mapped from outside inward in a familiar geometric way. What can be measured from outside is the gravitational influence and the radius of the no-return boundary that follows from that influence. For a non-rotating black hole, the horizon radius increases in direct proportion to mass. This relation is one of the cleanest features in black hole physics. If the mass doubles, the horizon radius doubles. If the mass becomes 1,000 times larger, the horizon becomes 1,000 times larger. This means that the largest known black holes are not only heavier than ordinary supermassive black holes, they are physically larger in the scale of the region from which light cannot escape. A black hole with a mass of tens of billions of suns has a horizon so large that familiar planetary distances become useful for comparison, even though the object itself remains invisible. Such comparisons help only up to a point. A black hole with this kind of mass may have a horizon diameter greater than the size of the solar system out to the orbit of the outer planets. This sounds like a statement about a gigantic dark sphere occupying a vast volume. In one sense, it is correct, because the horizon scale really is that large. In another sense, it can mislead, because the black hole is not a swollen object with texture, atmosphere, or a material crust filling that diameter in any ordinary way. The diameter describes the reach of the no-return boundary in space-time. It is a geometric consequence of mass and gravity rather than the measured width of a visible body. Mass also determines the depth of the gravitational well. A deeper well allows matter outside the black hole to orbit at higher speeds and to release more energy as it falls inward. This is why mass matters not only as a number, but as a guide to the entire surrounding environment. The broadline gas moves as it does because of the central mass. The accretion disk heats as it does because of the central mass, the scale of the inner visible regions, the strength of the redshift. And the efficiency of the quasar all depend in part on how much mass is concentrated at the center. The black hole does not have to be seen directly for its mass to structure the entire inner galaxy. At the same time, it is important to keep scale in proportion. Even one of the largest known black holes remains tiny compared with its host galaxy. A galaxy may extend across more than 100,000 light-years, while the horizon of even an ultra-massive black hole occupies only a minute fraction of that distance. The black hole is therefore huge only in local comparison. It is vast compared with the star, vast compared with a planetary system, and vast compared with smaller black holes. Against the full galaxy, and certainly against the wider universe, it remains compact. This contrast is part of why black holes are so striking. They combine extreme local concentration with limited overall extent. There is also a difference between the mass of the black hole and the mass of the material immediately around it. In a bright quasar, the accretion disk, broadline gas, and radiation fields are powerful, but their combined mass is generally still much smaller than the black hole's own mass. The central object dominates the gravity. This dominance allows astronomers to treat the surrounding gas as moving mainly in response to the black hole rather than the other way around. The surrounding matter shapes the light, but the black hole shapes the motion. In the most massive systems, this relation becomes even more pronounced because the central mass is so great. When black hole mass estimates are discussed, they are not measured with the simple certainty used for the weight of an object on Earth. They are inferred through models, line widths, luminosities, and dynamical reasoning. In nearby galaxies, masses can sometimes be constrained by directly measuring the motion of stars or gas in the central region. In distant quasars, especially the brightest and most remote ones. The estimate usually depends on the broadline region and the luminosity of the source. Observations indicate that some of these masses reach tens of billions of solar masses, but it remains uncertain exactly where the final value lies in each case, because assumptions about geometry and orientation affect the result. This uncertainty matters, yet even with generous allowance for it, the largest candidates remain extraordinarily massive. Rotation complicates the idea of size slightly. A spinning black hole has a somewhat different horizon structure than a non-rotating one, and the innermost stable orbits can lie closer to the center in the direction of the spin. This changes the geometry of the deepest visible region and can alter the efficiency of accretion. However, the broad statement remains: more mass means a larger horizon scale, and an ultra-massive black hole possesses a horizon of immense physical extent. Spin refines the picture, but it does not overturn the relation between extraordinary mass and extraordinary size. Another quiet consequence of great mass concerns tidal force. For a smaller black hole, the difference in gravity between head and feet near the horizon can be extreme. For a much larger black hole, that difference at the horizon can be less severe because the horizon lies farther from the center. This means that increasing mass does not simply make every effect more violently concentrated at the boundary. Some aspects become gentler locally, even while the overall size becomes larger. The black hole grows in horizon scale, but certain gradients become less abrupt at that outer edge. This is one of the reasons the physics of large and small black holes cannot be compared only by saying that one is a scaled-up version of the other. Mass also shapes time and light in its neighborhood. The larger the mass, the larger the characteristic scales over which relativistic effects matter. Gravitational redshift, orbital speed, and time dilation all become part of the observable environment across a wider region around an ultra-massive black hole than around a smaller one. The central engine is therefore not only more powerful in a simple sense, it is also more spacious in the region where strong gravity organizes the flow. Around the largest black holes, the dramatic physics occupies a larger stage. There is a temptation to think of size alone as the most astonishing fact. But mass is the deeper measure because it governs everything else. Size follows from mass. Horizon scale follows from mass. Orbital speed, radiative efficiency, and gravitational reach all trace back to the concentration of mass at the center. When astronomers say that a black hole has tens of billions of solar masses, they are describing more than heaviness. They are describing the curvature of space-time around one of the most concentrated and influential objects known in any galaxy. At this layer of the inward journey, the black hole is understood through proportion. It is larger than the intuition expects, yet still compact by galactic standards. It has no ordinary surface, yet it has a definable scale. It is weighed not by touch, but by the disciplined reading of motion and light. Its mass makes the horizon immense. Its size makes the local gravitational stage vast. And together they explain why some black holes seem to stretch the limits of what the mind finds easy to hold, even while remaining fully within the quiet logic of gravity. If the black hole now stands at a mass so large that it seems to resist easy belief, the question becomes how such a mass can be built. Growth is the final outward visible story before the inward path reaches the deepest unknown. A black hole does not begin at tens of billions of solar masses. It reaches such a state through accumulation across time. Matter falls inward. Other black holes may merge with it. The host galaxy changes, feeds, collides, and evolves. The result is not one sudden act, but a long history of gain, under conditions that are sometimes favourable and sometimes limiting. Observations indicate that some black holes in the young universe become very massive very early, and this remains one of the most demanding problems in modern astrophysics. There are several broad pathways by which a black hole can grow. The first is accretion, meaning the steady addition of gas and other matter from the surrounding environment. This process has already been traced through the reservoir, the host galaxy, the broad line region, and the accretion disk. When matter falls inward and crosses the horizon, the black hole's mass increases. If this continues over very long periods, the gain can become enormous. The second pathway is merger. When galaxies merge, their central black holes may eventually sink toward the new common center and combine into a larger black hole. This process can add mass in large steps rather than as a smooth flow. In reality, both pathways are expected to matter. Accretion seems simple at first, but it carries an important limit. As matter falls inward and radiates energy, the escaping light pushes outward on incoming gas. If the radiation becomes too strong, it can oppose the inward pull strongly enough to slow further growth. This balance is often discussed through the Eddington limit, which gives a characteristic luminosity where radiation pressure and gravity come into rough competition for ionized gas under idealized conditions. A black hole can grow rapidly if it accretes near this level for long enough. But if growth must proceed under this balance, then time becomes a strict constraint. The young universe does not offer unlimited time for a small seed to become an ultramassive object. This is why the earlier stages of black hole formation matter so much. A larger starting seed is easier to grow into a giant. If the first seed is only the remnant of a massive star, then repeated growth must be very efficient and sustained. If instead some black holes begin from direct collapse, where a very large cloud of primordial gas collapses into a massive black hole seed without first fragmenting into many stars, then the growth problem becomes less severe. Observations support the existence of very massive black holes at early times, but it remains uncertain which seed pathway dominates. Both stellar remnant seeds and direct collapse style seeds are studied, and neither has yet closed the question completely. The surrounding cosmic conditions of the early universe may help. Galaxies at that time often contain abundant gas. Interactions and mergers may be more common. Inflows toward galactic centers may therefore be stronger or more frequent than in many nearby galaxies today. A black hole that is already massive can also have an easier time attracting and holding a large inflow, especially if the host galaxy is itself growing rapidly. In this setting, a quasar phase can act as a period of intense feeding. If such phases repeat or last for long enough, the black hole's mass may rise dramatically. Observations indicate that some early quasars are indeed shining at very high luminosities, consistent with rapid growth. Yet rapid growth is not the same as unrestricted growth. Feedback complicates the picture. The radiation and outflows from an active black hole can heat or expel the very gas needed for continued feeding. In one sense, the black hole builds itself by accretion. In another sense, it can interrupt its own supply by becoming too active. This creates a self-regulating process in many models. Gas flows inward, the quasar brightens, energy pushes outward, and inflow may weaken for a time. Later, new gas may arrive and the cycle may continue. This stop-and-start history could still produce very large masses over cosmic time, but it makes the path less smooth than a simple picture of constant feeding. Merger adds another layer. Galaxies do not evolve in isolation. Over billions of years, many collide and combine. When this happens, their stars, gas, and dark matter halos reorganize into a larger system. If both galaxies contain central black holes, Those black holes may eventually approach one another through gravitational interactions with surrounding stars and gas. Later, at very small separation, they can merge and form one larger black hole, releasing gravitational waves in the process. This pathway does not rely only on gas feeding. It can increase mass by combining already grown objects. For the largest black holes in giant galaxies, repeated mergers over long timescales are expected to contribute significantly. Even so, merger alone is unlikely to explain the earliest extreme masses. To merge, black holes first need host galaxies and a surrounding structure mature enough to bring them together. In the young universe, there may not yet have been enough time for many large mergers to occur before some quasars already reach extraordinary mass. This is why accretion and seed size remain central to the problem of early growth. Mergers likely matter more and more as time passes and large structures become common. The final mass of an ultramassive black hole may therefore reflect both eras of rapid feeding and later episodes of merger-driven increase. The host galaxy participates throughout this story. A massive central black hole is not built only by local processes near the horizon. It depends on the galaxy's ability to gather gas, retain it, cool it, and funnel some of it inward. Bars, tidal disturbances, galaxy interactions, and global instabilities can all assist this transport. Star formation also matters, because it competes for gas and changes the surrounding environment through stellar winds and supernova explosions. The black hole grows within a living galaxy, not within an isolated machine. This means that explaining one of the largest black holes also requires explaining a large and effective galactic ecosystem around it. Observations indicate that black holes and galaxies co-evolve in some broad sense, but it remains uncertain exactly how tightly their histories are linked at the highest masses. In some systems, the black hole may appear unusually large relative to the surrounding galaxy. In others, the relation may be closer to expected trends. Measurements become difficult at great distance, where the quasar outshines the host. As a result, the growth story can be outlined with confidence in broad form while remaining incomplete in detail. This is often the case in extreme astrophysical systems. The main forces are known, but the exact sequence of events in any one object remains partly hidden. For the largest known black holes, the impression of impossibility often comes from compressing this long history into a single number. Tens of billions of solar masses seem abrupt when stated alone. The number appears less sudden when unfolded into repeated acts of feeding, intervals of quasar brightness, mergers across cosmic time, and perhaps a large initial seed formed under unusual early conditions. The growth is still remarkable. It is not ordinary. But it does not require new everyday physics. It requires known gravity operating over immense time within rich environments, sometimes near limiting rates, and perhaps beginning from favourable starting points that are still being investigated. At this stage, the black hole has become a record of accumulation. Its mass preserves the memory of ancient gas inflows, galactic collisions, and long periods of central activity. Observations show the result more clearly than the full path. The end product is visible in the quasar and in the inferred mass. The detailed biography remains partly uncertain. Still, the broad answer is calm and physical. A black hole that feels impossible grows by taking matter in, by joining with others, and by doing so within a universe that, especially in its earlier ages, offers moments when growth can proceed on the larger scales known. The inward path now reaches the innermost unknown. Everything outside the event horizon can be studied, at least in principle, through light, motion, and the comparison of observation with theory. Everything within the horizon belongs to a different category of knowledge. It is not merely hard to observe, it is hidden from outside observation by the structure of space-time itself. No signal returns from within. No beam of light carries direct news outward. The black hole that has been approached through galaxy, gas, disk, radiation, and horizon now becomes something that physics can describe only in part. According to general relativity, matter that crosses the event horizon continues inward. If nothing interrupts that description, the inward paths lead toward a singularity. A singularity is a place where the mathematical description of space-time curvature becomes formally infinite, and the usual equations cease to provide a complete physical account. This idea is often presented as though it were a finished picture of a real interior object, but in careful science, it is understood more modestly. General relativity predicts that under its own rules, continued collapse leads to such a state. At the same time, most physicists take this as a sign that the classical theory has reached its limit, and that a fuller description must include quantum physics as well as gravity. Quantum physics describes matter and energy on very small scales. General relativity describes gravity and the large-scale structure of space-time. Both theories are highly successful in the domains where they have been tested, yet they do not sit together in a complete unified framework under the most extreme conditions. The deep interior of a black hole is one of the places where this incompleteness becomes impossible to ignore. Observations indicate that black holes exist, that event horizons are real in the astrophysical sense, and that matter falls inward beyond visible return. It remains uncertain what exact physical state replaces the classical singularity in a complete theory of quantum gravity. This uncertainty is not a weakness in astronomy. It is the honest edge of present knowledge. Outside the horizon, evidence is rich. Inside the horizon, theory continues, but direct test becomes extremely limited. Some approaches suggest that the singularity may be resolved into a finite quantum state. Some suggest that space-time itself may have a different structure at the smallest scales. Some ideas propose that information is preserved in ways not yet fully understood, even though the ordinary classical picture hides it from outside view. These ideas belong to active theoretical research. None has yet become a settled observational conclusion for the interior of astrophysical black holes. Even the meaning of time changes in this discussion. Outside the horizon, time and distance can be described in ways that allow stable observation and exchange of signals. Inside, the geometry of space-time is arranged so that movement towards smaller radius becomes as unavoidable as movement toward the future is outside. This statement is a mathematical feature of the classical solution, not a poetic one. It means that once the horizon is crossed, the inward direction is not simply one option among many. It becomes part of the causal structure. In that sense, the black hole interior is not merely dark. It is a region where the ordinary outward choices available in the external universe are no longer present. For an ultramassive black hole, this hidden interior is not more accessible simply because the horizon is larger. The scale changes, but the concealment remains absolute for outside observers. A larger horizon means the boundary of no return encloses a greater region, but it does not offer a window inward. The inner unknown remains unknown whether the black hole contains a few solar masses or tens of billions. Mass changes the horizon scale and the surrounding astrophysics. It does not remove the basic separation between the observable exterior and the inaccessible interior. There is a second uncertainty tied to the first. Black holes raise deep questions about information, meaning the physical details that describe the state of matter. If matter falls into a black hole, and the black hole later loses mass through Hawking radiation over inconceivably long timescales, what becomes of the information about what fell in? Hawking radiation is a theoretical quantum process by which black holes are expected to emit a very faint thermal glow due to quantum effects near the horizon. For supermassive and ultramassive black holes, this radiation is far weaker than the cosmic background radiation at the present time and is completely negligible for the active quasar phenomena already described. Yet in theory it matters because it connects black holes to quantum mechanics and to the fate of information. It remains uncertain exactly how this question is resolved in a full theory, though most physicists expect that the underlying laws preserve information in some form. Because the black hole interior cannot be inspected directly, science proceeds by consistency. The external gravitational field is measured, the motion of matter outside is studied, the presence of the horizon is inferred from the disappearance of further signal. Theoretical models are then judged by whether they agree with everything known outside while remaining mathematically coherent inside. This is a different kind of scientific work from imaging a planet or sampling a rock. It is an investigation by boundary, where the edge of the visible system is known well enough to constrain what any deeper account must respect. In this final region, language also becomes more careful. It is easy to say that there is a point at the centre where all the mass is located, but this is too simple to carry the full meaning. In general relativity, the singularity is not a little ball hidden inside the whole. It is a breakdown in the classical description of space-time reached by inward-directed trajectories. Once quantum gravity is considered, even that language may change. What is safest to say is that current classical theory predicts an inner limit, where its own equations no longer provide a complete physical description, and that no direct observation yet tells exactly what replaces that limit. The great black hole that seems impossible from afar therefore ends in scientific understanding, not in a final visual picture but in disciplined silence. The host galaxy can be described, the gas reservoir can be traced, the broadline region can be measured, the disk can be modelled, the hot corona can be inferred, the event horizon can be defined as a physical boundary of no return. Beyond that boundary, certainty narrows. The strongest statement is that the interior exists as part of the black hole solution, and that present theory points toward conditions where known descriptions fail to remain complete. This is fitting in a quiet way. The largest known black holes are not only objects of mass and light, they are also boundaries in human knowledge. They show how far observation can travel by following radiation across billions of years. They also show where observation must stop, not because instruments are weak, but because the universe itself withholds direct signal from beyond a certain line. The black hole becomes both an astrophysical object and a reminder of method. Science reaches it through evidence with great success, and then meets a region where evidence from outside can go no farther. At the end of the inward journey, the impossible feeling softens into something more stable. The black hole remains immense, its scale remains difficult for the mind to hold all at once, yet its outer behaviour fits within known gravity, known radiation, and known cosmic history. Even while its deepest interior remains unresolved, observations indicate what can be trusted. Theory extends further, and then admits its present limit. In that balance between knowledge and uncertainty, the giant black hole rests as one of the clearest examples of how the universe can be both understandable and still unfinished. The long path inward now becomes still. The galaxy remains spread across its dark halo. Ancient gas continues its slow motion through wide and quiet distances. The quasar light, once so bright against the deep sky, settles in thought into the simple fact of falling matter giving off energy before it vanishes. The broad lines of fast gas, the great rotating disk, the hot inner radiation, and the final boundary of no return all remain in place, ordered by gravity and measured through patient light. At the centre of this calm arrangement rests a black hole of such mass that it first seems beyond belief, yet step by step it becomes less like a fantasy and more like a consequence. The universe allows matter to gather, it allows galaxies to grow, it allows light to cross billions of years carrying precise information. It allows gravity to shape gas into rings of heat and motion around a darkness that cannot shine. In that steady logic, the giant black hole takes its place. Much remains uncertain in the deepest interior, and science states that uncertainty plainly. Observations indicate the outer structure with confidence. It remains uncertain what exact form the hidden center takes when gravity and quantum physics must be joined completely. Even so, the unknown does not undo the known. The visible regions are enough to show an object both real and immense, both distant and exact, so the mind can leave it there, not as a monster in the dark, but as a quiet center in a far galaxy, seen by ancient light and understood in layers. The outer universe holds it, time carries its signal, gravity shapes its surroundings. Beyond the final boundary, silence begins. Outside that silence, the cosmos continues in slow motion, full of dust, gas, stars, and the patient reach of human thought moving inward as far as light allows.